Chapter 1, Section 3, Organizing Data. So key ideas in this section: why is organizing data an important science skill? How do scientists handle very large and very small numbers? And how can you tell the precision of a measurement? Because scientists use written reports and oral presentations to share their results, organizing and presenting data are important science skills. Scientists are always wanting to share what they've learned, so they gather new knowledge by studying something, and they want to share that out. And so making sure that your data and thoughts are organized is important in order to get the point across and to be able to share those results. So one of the ways that we organize data are through the making of graphs, and the different types of graphs is what we're going to look at here. The first type of graph we're looking at is a line graph, and line graphs are best for showing continuous change. Showing how a variable changes over time is always going to be used for a line graph, and then any other type of continuous change you would use a line graph to show. And so line graphs, you have your dependent variable and your independent variable. The dependent variable is the values for the graph depend on what happened in the experiment. So the dependent variable is what you measured. It depends on what you changed. So maybe like if I was doing a line graph over which, like the height of a plant that was growing, the dependent variable would be the height of the plant. And so we have to wait and see how tall the plant grew before we can determine the values we would use on the line graph. And so dependent variables are always plotted on the x-axis, the bottom of the line graph going horizontally. Independent variables are set before the experiment takes place. So the independent variable is like what you're measuring. So with the plant, if I was going to measure, the height that it grows throughout a month, I might set my independent variable that I'm going to measure it every day. And so that value is set before I actually start the experiment. And the independent variable is plotted on the y-axis, and so that is the vertical axis. Here's an example, the volume of a gas over time. And so the time would be your dependent variable because that's on that bottom on the x-axis. Volume of the gas is the independent variable, and it's plotted on the y-axis. Bar graphs, we're familiar with those, or we should be. Bar graphs are used to compare sets of data or to compare items. A bar graph is useful for comparing similar data for several individual items or events. I usually like to make bar graphs to show how different classes did on exams. So like I have 2 sections of ICP this semester. I'll probably show like a bar graph to show what first period did versus second period. And you can see the difference. A bar graph can make clearer how large or small the differences in values are. So here's an example of bar graphs, melting points of common metals, and you can just very quickly look and see iron has the highest melting point, lead has the lowest melting point. Much quicker than if you were reading the data table. The other type of graph that we look at are pie graphs or pie charts. Pie charts show how parts of something relates to the whole. A pie graph is ideal for displaying data that are parts of a whole. So like if I took a whole group of something and I was showing how a certain part relates. Data in a pie chart is presented as a percent. So this particular one is showing what a winter coat is made out of. And so 66% is nylon, 30% polyester, 4% spandex. Another way we organize data is by writing numbers in scientific notation. And this is useful because it reduces the number of zeros in very big and very small numbers. Now, when I'm talking about a small number, I'm not really talking about negatives. I'm talking about small decimals. You can express the values as simple numbers multiplied by a power of 10 in a method called scientific notation. Scientific notation is a method of expressing a quantity as a number multiplied by 10 to the appropriate power. Now, in freshman year, you learned about scientific notation in your algebra class and in your science class, or you should have. And we really just focus on how to put numbers into scientific notation and take them out. Scientific notation becomes very useful when we're making calculations. So we can take a big number and very simply multiply it by another really big number if we have everything written in scientific notation. When you use scientific notation in a calculation, we follow the math rules of powers of 10. So when we multiply numbers that are in scientific notation, we add the exponents, and when we divide, we subtract the exponents. We'll look at that in more detail on another day when you're practicing that skill. Another thing that we do to organize numbers in science is by using significant figures. This is probably a brand new topic to all of you, so we're going to spend a whole nother day just looking at significant figures, so don't stress out if you're still confused after this. Scientists use significant figures to show precision of a measured quantity. What does it mean if something is significant? Think about that a little bit, like a significant thing. It means it's important. So a significant figure are the important parts of a number, basically. So significant figures show the precision of a measured quantity. Precision is how exact the measurement is. A significant figure is a prescribed decimal place that determines the amount of rounding off to be done based on the precision of a measurement. It is basically what are the important numbers in the measurement and where can I round that measurement to. Precision differs from accuracy, so that's another word you need to know. Accuracy is how close a measurement is to the true value of the quantity that is measured. So some examples in this first picture of a ring toss game, this person had good accuracy, they were near the target, and good precision because all of their rings were close together. In this next picture, this person had good accuracy. They were close to the target every time, but they had poor precision because their rings are not hitting the same place. Here, we're hitting the same exact place, but we're not close to the target. So this person had poor accuracy. They're far from the target, but they had good precision. They're hitting the same exact place every time. And in this picture, this person is that's like me if I was playing. They have poor accuracy and poor precision. They're not close to the target, and they're all over the map. So that wraps up our chapter 1, section 3 notes. If you have any questions or you need extra help, as always, you can email me, message me on Google Classroom, or schedule a Google Meet with me on Google Classroom, and I'll be glad to answer any other questions you have.